Let's say a particle is attracted to a fixed center by a force that scales as the distance to some power. For example, Newtonian gravity or Coulomb force are inverse square laws, so they have the exponent alpha equals -2, and Hooke's law has the exponent to be 1. It turns out these exponents form specific pairs. One of them is 1 and -2, another pair is -7 and -4, but the inverse fifth power law pairs with itself. The only unpaired exponent is -3, which makes the inverse cube law special. But why these pairings? It started with this Swedish guy, Carl Bolin, who identified the first pair using complex numbers. The big picture is this. Consider the trajectory of a particle under this alpha equals 1 force, that is, the magnitude of the force is proportional to distance, or Hooke's law. Since the trajectory is two-dimensional, we can treat this as being on the complex plane. So instead of saying this point is AB, we say this point is A plus BI, and this fixed center will be 0. If we take the square of every point of the orbit, then we should get another curve. But this curve will be a possible orbit under a new force with alpha equals -2, the inverse square law. Of course, you can also square root to go back to alpha equals 1. In this sense, these forces are dual to each other. Bolin worked this out in 1911, and the squaring transformation is usually called the Bolin transformation. But then Arnold and Vasiliev generalized the argument to all exponents to form different pairs, each pair with their own transformations. These transformations are what's known as conformal transformations, so these pairs are sometimes known to be conformally dual to each other. Let's first see why we can just square the track to switch between the two forces. We're gonna use this formula in the previous video. Don't worry if you haven't watched it, here is a brief recap. The idea is to determine acceleration purely from the geometry of the orbit, if the acceleration always points towards the center. Starting at point P, this particle arrives at r after time delta t. We can break down the displacement into the velocity times delta t and have acceleration times delta t squared. That's Taylor expansion up to second order. Because we assume the acceleration points towards the center, these two green segments are parallel. This is how to geometrically construct the point Q given point R. But based on this length, we can express the acceleration in terms of QR. However, delta t is not geometric, so we need a trick, which is to consider the area of this triangle. If we denote the vector OP as x, whichever direction doesn't matter, then the area of this triangle is half the magnitude of the cross product of x and v delta t, which is half h delta t, where h is the angular momentum if we have unit mass. And we are going to assume unit mass from now on. Then we can rewrite delta t in terms of this area and h. Plugging this back into the previous expression for a, and rearranging a bit, we get this formula for acceleration. Since this h is angular momentum, it is a constant, so once we set a value to h, this formula only relies on the geometry of the orbit. Also note that the ratio should be understood as the limit as delta t tends to 0. Now let's treat all these on a complex plane, square the whole setup, and see what happens. This is the result of squaring everything. To compute the acceleration associated with the new orbit, we can't just replace q and area as those new ones in the formula. After all, the point q should be constructed on the tangent in the formula. But the tangent curves up when we do the squaring transformation, so we shouldn't directly use the point q prime. Instead, the corresponding point should be somewhere along the new tangent. Let's call this point q tilde. Where exactly is q tilde then? In the previous construction, we need QR to be parallel to OP because the acceleration points towards the center. Similarly, for the new orbit, Q tilde should be the point on the new tangent such that Q tilde R prime is parallel to P prime O. So the new acceleration should be computed with this point Q tilde, and the new area should also involve this point Q tilde. We should now focus on computing what these quantities are, starting with the numerator. Let's use little p to denote the complex number associated with the point capital P. Then Q should be P plus V delta t, where this V is also a complex number corresponding to the velocity vector. R would have an additional half a delta t squared, and again, this a in this context is also a complex number that corresponds to the acceleration. We assume that the original setup before squaring is an orbit under a force whose magnitude is proportional to distance. Equivalently, the magnitude of acceleration is proportional to distance. Then, as complex numbers, we can write a equals negative kp for some real constant k. In this illustration, k is positive. Now replace a as negative kp in the complex number associated with the point R. We then try to square this whole setup, so we just square the numbers associated with p, q, and r. The point p prime is now little p squared. The point q prime is now the square of q, which is calculated to be p squared plus 2pv delta t plus v squared delta t squared. Finally, we square r, but only collect all the terms up to the second order, and this is the result. A pretty fortunate thing to notice is that q prime and r prime only differ by this term, negative kp squared delta t squared. So this direction is given by negative kp squared delta t squared, but since k and delta t are real, this points in the negative p squared direction, the same direction as p prime to O. After all, p prime is little p squared in this complex number picture. All this is to say that these two segments are indeed parallel. That's good, because ultimately we wanted to compute the length q tilde r prime, where q tilde is formed by this parallel line from r prime to the new tangent. The fact that q prime r is parallel means q prime is actually in the middle of this segment, so we have already computed a part of the length we wanted. This q prime r prime part has length k mod p squared delta t squared, and we just need this remaining part q tilde q prime. Let's clean the whole setup a bit before we compute this remaining bit. It's quite tempting to think that q tilde exactly corresponds to p squared plus 2pv delta t, but that's not quite true. If that were true, this segment would point in the direction of v squared, but then p prime o points in the direction of negative p squared. These two aren't necessarily in the same direction, so q tilde doesn't correspond to this number. Nevertheless, it is still worth considering the point p squared plus 2pv delta t, so let's denote this point as a. Because a is a first-order deviation from p prime, it does lie somewhere along the new tangent, just not necessarily exactly at q tilde. Let's say a is somewhere here. We'll see how not to scale this is, but let's say for now a is here to illustrate the argument. This time, because a and q prime differ by this v squared delta t squared term, the segment joining the 2 points will point in the direction of v squared. We've also seen previously that q tilde q prime should point in the direction of negative p squared because it is parallel to p prime o. Finally, being on the tangent, the direction from a to q tilde is pv, because that's the direction to go from P prime to A via the tangent. Now you might know where this is going and how not to scale this is, because we will show that these two angles are the same size. Let's start with the lower angle, which can be computed with the help of the positive real axis, because it's the difference between these two angles. The larger angle is precisely the argument of the complex number v squared, and the smaller angle is the argument of PV. So this angle is the difference of the arguments. From the operations of complex numbers, it is the argument of the quotient of these complex numbers, which is the argument of V over P. We can use basically the same argument for the upper angle, just that this time it's the difference in arguments of other complex numbers. But the result is the same. The upper angle is also the argument of V over P. Because these two angles are the same, we have an isosceles triangle, meaning Q tilde Q prime and Q prime A have the same length. Again, this illustration is not to scale. We know that the length of AQ prime is the modulus of V squared delta T squared, so the length of Q tilde Q prime is also that. Going back to why we were doing all these, we were looking for the new acceleration of the new orbit. We have previously derived the length of this bit, Q prime R prime, from noticing that they differ by kp squared delta t squared up to second order. And now, we also have the remaining length mod v squared delta t squared. Q tilde R prime is the sum of these two segments, which looks a bit suspicious. If I massage the expression into this, does it ring a bell? The first term is the kinetic energy of the original setup since we assumed unit mass, and the second term is the potential energy of the original setup because in the original setup the acceleration is proportional to distance, that is Hooke's law. So this bracket is the total energy of the original setup, which is a constant, denoted as E. The length Q tilde R prime is then 2E delta T squared. That's the numerator of this formula done, and we are left with the denominator where we need to compute the area of a triangle. The triangle is this one, bounded by Q tilde, P prime, and O. There are many ways to compute the area, but we choose this one, where we compute half the product of two lengths and sine of the included angle. The length OP prime is mod P squared because P prime is represented by the complex number P squared. The other length is a bit trickier, but we can go back and see what the point R prime is, and given that we have just deduced this length as 2E delta T squared, Q tilde is still P squared plus 2PV delta T plus some terms of higher order that we don't care this time. So this length is 2 mod P mod V delta T plus higher order terms. To compute the included angle, we use the technique seen a couple times by now. The tangent direction is PV, and the direction from P prime to O is negative P squared. So the included angle is the argument of the quotient negative P over V. Combining all these together, we get the new area. However, this expression is still a bit clunky. To simplify this, we can use the original setup and compute the original area in the same way. The old area was half angular momentum times delta t. The length OP is mod P, the length PQ is mod V delta t, and the angle can also be computed in a pretty similar way as before. The direction along the tangent is given by velocity v, and the direction towards the center is negative p, so the included angle in this case is also the argument of the quotient negative p over v. With this old area expression, we can simplify the expression for the new area, which is angular momentum h times mod p squared delta t if we ignore the higher order terms. Finally, we substitute everything back into the formula for the new acceleration and obtain some angular momentum ratios times energy divided by mod p to the 4. Since angular momentum and the original energy is conserved, this is inversely proportional to the new distance squared, because the new distance from origin is mod p squared after the squaring transformation. Before squaring, we assumed the acceleration is proportional to distance, or Hooke's law, and we have shown that after squaring, the acceleration follows inverse square law. Can we generalize this? What if we started off with acceleration proportional to some other powers of distance instead? Can we end up with another one, but with a different exponent beta? Of course, it might not be squaring, it could well be some other nth power. This can be done if we choose alpha, beta, and n cleverly. The generalization is very similar, so I'll go through a bit more quickly. We also start with these points p, q, and r, but this time the acceleration is proportional to distance to the power alpha. So as complex numbers, the acceleration a is negative kp times mod p to the power alpha minus 1. This is so that the direction still points towards the origin, while the magnitude is still proportional to mod p to the power alpha. Then we get this expression for the point r. Now we take everything to the nth power, expanding everything to second order in delta t. The computation is slightly more tedious, but still just using the binomial theorem. Essentially, the length of q prime r prime is given by this extra term, and the length of q tilde q prime is the same as this second order term in q prime, using the same argument of the isosceles triangle as before. Now we combine these lengths and massage the expression, where we see something that kind of looks like the total energy of the original setup. Since the original setup obeys alpha power law, the potential energy from this force is the integral with respect to the distance. So in order for this bit to be total energy, we would need 2 times n minus 1 and alpha plus 1 to be equal. If they are equal, then we have these expressions for length of q tilde r prime. The final thing to compute for the new acceleration will be the new area bounded by O, P prime, and Q tilde. Similar to the previous computations, we compute the area with this formula. Without the detailed explanations as before, the length OP prime is mod P to the n, and the length of P prime Q tilde is n times mod P to the n minus 1 times mod V. The angle doesn't matter too much, because similar to the squaring case in the original setup, the old area has the same angle anyway. The expression for the old area then helps us simplify the expression for the new area. Combining everything so far, including the length of q tilde r prime, the new acceleration is this. If we ignore constants like energy and angular momenta, then this new acceleration is proportional to mod p to the power 2 minus 3n, which is the new distance to the power 2 minus 3n over n, because the new distance from the origin is mod p to the n. Let's denote this new exponent beta. Combined with the relation between alpha and n we impose to make all these work, we now have two relations between n and the exponents alpha, beta. If we know alpha, then we can solve for n and then beta So for a given exponent alpha, we can work out its partner beta using these two relations. The pairs of exponents in the beginning are some integer solutions to these relations. There is one special case in which we start off with the exponent -3. Then both sides should be -2, which forces n to be 0. But then the denominator in beta is 0, which is bad, so we can't really start with alpha equals -3. So the exponent -3 doesn't have a partner in this sense, which makes the inverse cube law special. There is also another edge case which is debatable, which is when we start with -1. Both sides are 0, so n is forced to be 1, which doesn't seem problematic, but when doing the transformation z to the n, if n equals 1, we haven't actually transformed. So I would argue that -1 is also unpaired, although most literature consider this trivially self-paired. Now I want to mention two things. While I relish this geometric explanation, you might find it easier to do it purely algebraically. I don't like that nearly as much, not just because it doesn't give a lot of insights, but also that we need to reparameterize time in such a specific way that I can't see why anyone would try that. The geometric explanation we gave actually gives the reason why. In the squaring transformation, we've shown in the new setup that this bit is twice the energy times delta t squared. But this should be the second order deviation with the new acceleration and new time tau. We've computed the new acceleration before, so we can substitute that into the equation, which yields a relationship between old time t and new time tau. And that's why we adopt this specific kind of reparameterization. The other thing to mention is that we can generalize these pairings even more. Even though alpha equals -3 is unpaired in this sense, if we do a logarithmic transformation instead of raising to some power, it does give another force, just that this force doesn't point towards the center. There can be more general conformal transformations that relate different forces, and we'll talk about this general duality in the next video. Thanks for the patrons, and don't forget to like, subscribe, comment, and I will see you next time. Bye!